Hi, hello Node people. My name is Nikolay, I'm from Russia, you know, St. Petersburg. And I'm working in Grid Dynamics, and we do replatforming using Node.js for large US e-commerce companies such as Nike, Kohl's, Macy's, American Eagle, and so on. And this is an enterprise development, and it has its own features. Node is very popular and widely used at different levels. We have days of high load, like Black Friday Eve, and that leads to permanent growth of functionality. And often we have a growth of performance, and therefore, whatever is fast today will be slow tomorrow, as the demands can only grow. And there is a problem. It's a heavy loaded main thread because each project was different with its architecture, with its technologies, but thread is busy. Why it's so? Even in monolith or microservices, we have a Z part, the common part which contains metrics collection, garbage collections, logging framework that perform in main thread and can block the event loop. What does it mean? Guys, imagine a usual situation. Node.js server handles user requests, and it makes a synchronous call to backend, to databases, response is returned back, and the callbacks line it up for the execution. But there is a long rendering in the first callback that blocks the event loop. Server does not accept new requests. But the most crucial is that all the other callbacks with the remaining ready responses are sessions of different users who are waiting in the queue at that moment. And it reminded me of a situation when I tried to buy a ticket for the last World Cup and spent 4 hours in a queue just to buy a ticket. That's not good. And more often and longer we block the event loop, more often it's blocked, so delay grows, response grows, and throughput is reduced. And there is a way out. We can use scaling, right? We can run an application in a cluster using multiple cores. We can run it in multiple servers. We can dynamically manage load, right? You can use a web server, reverse proxy. Yes, and this is a way out, but not a solution to the problem. Because with the growth of delay, response time grows. And when it reaches a critical level, user will just leave aside. And that's what we don't need it. Nobody like it. And to figure out which operations are performed in main thread and can block it, we need, similar to dispersion of a beam of light in physics, pass the main thread through the profile prism to decompose it into operations. And those are garbage collections, computations in JavaScript on CPU, deserializations, framework, logging, matrix collection, server-side rendering. And this is a latency. Moreover, guys, users don't need matrix collection, logging. That's what we need. But users pay for it with their time, right? Take, for example, garbage collection, which works on the principle stop the world. In 1959, the first garbage collector in Lisp said, hey, the world is mine now, because it blocks the server. And every time, imagine that gray bar is our main thread in Node.js. And every time when garbage collector need to collect garbage and clear memory, application code is suspended for that. But perfectly understanding the problem, a team made incremental collection to block a server for a shorter period. And they achieve a higher performance in Node with that. But collection still performed in a main thread. And they gradually, a team, offload all those operations to separate threads, to V8 THREADPOOL. So we got new garbage collector Arino core. Cool. We have parallel mark sweep, parallel scavenger, parallel mark evacuate with less performance overhead. So what they did, they offloaded those operations to separate threads from the main thread. And we can execute more JavaScript. But 50 years after the creation of the first garbage collector was created Node. And now the world belongs to the Node.js CPU-bound task because they simply block the server. And inspired by V8 team approach, I suggest you to optimize or even parallelize the remaining task. But how can we do that? So the first solution is just to move something to another service. For example, hey buddies, this code is too heavy for my Node app, let's perform it somewhere, right? This is a good production approach. But if we don't have such opportunity, we can use a native solution to create a child process, right? We are fork and delegate tasks to it. But we have to serialize that at any time when we want to send to child process. And there is a solution, native solution to create a native module, write it in C++. But this is a C++, and we don't write in C++, we like JavaScript. And there is a solution from NPM that allow us to create V8 instances and run JavaScript there in parallel. And in this year, Anna has transferred such functionality to Node. And now we have a multi-threading in Node.js. So first, initially it was a solution like web worker threads, Napa.js, alias, and now we have web worker threads. And it's very helpful when resources are limited and there is no way to scale. For example, IoT, modules, when task is difficult to separate from application context. And tasks like parsing, hashing, HTML modification, because it's required data parsing again. So I wrote a small application. It's just a prototype or usual production applications, and that allow me to configure my application with different task frameworks, loggers, APM agents, and I'll show you the code. So the root place is server factory that allow me to configure different cases with different libraries. For example, the first one is a cluster. Do you see? Cool. With Express, with Winston Logger to Elasticsearch, with CPU task, and asynchronous call, and with JSON serialization task. So I have multiple tasks with CPU, for example, with the same abstraction interface, and for example, parallel CPU computations with 2 workers. So, and common code in controller. So, this is a common code for each framework, and I run 2 CPU tasks when I'm trying to find a subarray of numbers which sum is 42, and the longest is which sum is 0. Okay, I do logging, and I perform serialization, so parse, encode, decode, and so on. So, and running this application, for example, in a cluster with case 1, where we have Express in each worker Winston, in process CPU task, and just a simply JSON stringify, and do a stress test just for 5 seconds. Okay, we will have only 141 requests per second. It's a small, it's a throughput, and with a latency for 500 milliseconds. And our task is improved. So let's go to the remaining task. Let's go to deeper to the computation. So I did a lot of measurement, and the average was 119. That's what I will use in presentation. So let's go to computations. Everything works incredibly fast until we calculate something in JavaScript on CPU. Unsuccessful choice of algorithm. Merging objects, parsing, hashing, minifications, all those tasks block the remaining ready responses in a queue. And there is a solution to prepare process pool. We can use a child process to make a fork. We can pass data through the in-process communication channel. And there is a common pattern that consists of 3 queues. Pool of workers, pool of active workers, and pool of waiting tasks. But to send data, we have to serialize it and parse every time. And to avoid it, we can use new solution. We can use worker threads we also need to prepare that thread pool, but we have here a faster communication between a message channel in the same process. So, and if we will run our application with two workers inside, thread workers inside each application and in a cluster, we can achieve performance 3 times faster than in process that it will works in process, and it's good. Sorry. And I know a real project in production. They already use threads in production, and they achieve twice performance. Let's go to deserialization. Every time when we need to communicate with backend, with browser, with database, we have to serialize or parse data. And usually we use JSON because it's human readable and it's native for web and Node. But there are also a lot of other useful formats like protobuf, IRO, binary formats. And if we have different platforms, if our architecture like Java, Python, Go, we have to make decision with a format will work faster there too. Because in such environment, in different environment, protobuf works 6 times faster than JSON. But since there is a JavaScript conference, right, we'll talk about JSON in JavaScript environment, where it's well optimized by V8 team. But the second disadvantage is that everything depends on type of data. And the slowest of all, JSON work with numbers, with fractional numbers, with float. And protobuf parse data twice faster. But while JSON serialize and parse text, protobuf decode and encode binary format with data schema. And if we will use JSON with data schema, we can parse serialize twice faster and parse 30% faster. That's good. Much better with strings, because unlike protobuf, for JSON they are simply copied. It's a text. But anyway, parse works slower than protobuf. But if we will use JSON with schema, we can parse 3 times faster. 3 times faster. So that JSON is not completely awful. And if we run our application with a library like fast.json stringify or turbo.json parse, we can increase plus 27% requests per second. Awesome. Let's go to the framework. So framework, it's a massive layer of abstraction, right, with a huge functionality out of the box. But however, we include framework in our application, we lose in performance. And there is a solution to use first to write in native HTTP server or to use faster framework. For example, Fastify. So those guys who created Fastify, they solved two issues, two problems, two bottlenecks: the router and the serialization. And for example, to find a right route in Express, we have to go through the array of all routes to find the right one. But Fastify keeps routes in a radix tree structure that works 5 times faster. And also they have a fast.json stringify out of the box. That's very cool. And the point is not that Fastify is better than Express. No, we also can use a core framework that also has a fastest router, for example. But Fastify has 2 components out of the box, and it's too convenient to use it in an example. So running application with a different framework like Fastify, we can increase in performance plus 20% requests per second. And the current rate is 922 requests per second. Let's go to logging. So guys, should we really care about logging performance overhead? Unfortunately, yes. Because to write a log, we have to format message, we have to serialize it and manage transport logic. And sometimes writing can be performed synchronously depending on the operation system. And all loggers work in process, so they do all their work in the main thread, right? And can block the event loop, especially for serialize a message. But there is a solution to offload part of this logic to a separate process, right? To make a second node up and pipe the messages through the std out stream to second node logger transfer. And if you will run our application where in a cluster where each application has a logger via transport, we will increase plus 17% per request per second with off-process logger transfer. Good. Let's go to the performance monitoring. Performance monitoring is an integral part of application in enterprise. It's very helpful, and usually we use agents with automatic metrics collection. They collect a lot of useful metrics, request duration, errors, garbage collection, and even event loop delay. It's very good, but all those solutions are work in main thread and block our server. So they make performance overhead. And there is a solution, I guess you know, to offload part of logic of agents to a separate process, and just to send from the main thread a raw event with raw data, we send via queue to that process. And in that process, we do format, we do aggregation, and we handle transport logic to database, to server, for example. So we moved logic and responsibility to a separate process. And using this approach with lightweight agents, we can achieve plus 25% requests per second. And the current rate is 1,347 requests per second. My favorite part, server-side rendering. Server-side rendering is very convenient on Node, right? We like server-side rendering, but for convenience we have to pay, and unfortunately this is a very expensive operation. Why? Because it's typical CPU-bound task, and that can't be performed 100, 200, even 500 milliseconds. And if our rendering takes 500 milliseconds, how much requests server can perform per second? 2? And how many servers do we need in this case? And there is no limit for scaling. But we can use streaming rendering, because a streaming response was initially implemented in Node, and React provided this functionality from their side. So they created streaming rendering, and now we can render a page by portion. We block server for a shorter period, and moreover, we can render multiple pages in the same time. It's very cool. But in that case, rendering still performed in a main thread. So we didn't offload anything to separate threads, right? And there is a solution to make the separation parallel. We can divide our page for components and move some of that to microservices. So we can render, for example, the header in the first microservice. To render the body in the second, we can cache some of them, right? And so we make a parallel rendering in that case. And there is a new solution. Since we have a threads, we can rendering is a stream, it's asynchronous. We can move those stream to worker threads, but it's experimental. And we have a project with 16 React in production now, and it allows us to achieve twice performance with this rendering. It's pretty awesome. So what we did, we start from 119 requests per second and achieve 1,350. Let me try to repeat it. So I will run the last case. Okay. We have a Fastify worker, we have Pino logger with off-process transport. We have a parallel in threads CPU task. We have a fast JSON stringify library which works with JSON schema. And we have a lightweight APM performance monitoring agent. And running this application in a cluster for a shorter period, 5 seconds. Yeah, it's 1,318. So what we did, on the same machine, running the same code, we achieve performance. So, and even in the past, we should have a 10 server. Now we can do the same task on one server, for example. Yeah? So let me repeat one more time again. So logging, we move it to a process, separate process, child process. APM agent to the separate process, communicate with a queue. CPU, more interesting, we have a lot of cases here. The first one is experimental new V8 worker thread. Also we can use the LIBUV, we can run modules in C++ there and use their threads. And we can use the child process as well. V8, garbage collector, they did all work for us. They created a THREADPOOL, so it runs in parallel. And I/O is performed in LIBUV THREADPOOL. So I guess you know what we did. So we offloaded CPU-bound task, right? We don't need it. We got the monitoring agent. We don't need it. Loggers transport. Our application is too slow. We don't block event loop. We use streaming rendering. And we achieve a high performance. But be careful, most of features are experimental, like threads, and you know what was in the final of this movie. Yeah? So, in which order we should to do that? So we need to start from the longest task, like CPU or rendering, and after that we should to go to the smaller. And only in this case we can achieve performance improvements, right? So finally, using this approach, even for one case, for example, for logging or, for example, for rendering, you can achieve a high performance, a 5, 10, and more. Because in my example, I had a request with the same time. But if you will have a cached result, which cannot be blocked by a longer request, you will achieve a high performance removing a blocker, right? So this is the resources. I will upload my presentation to Twitter. You can find it there. And thank you.
Thank you, Nikolay. Thank you, Nikolay.